3 is a week from this Friday. So what would that be? A week from the 28th. So I think that's like December 5th, maybe. Um, um, and uh, the topics are going to be everything up through the second law. So that means none of the stuff that we're starting today, nothing on the Rankine cycle. Any questions about the test?
We'll have the same formula sheet as we had in the last couple of
Yeah,
times.
yeah. Anything else?
I think we went over this last time, but you said best way to kind of like go over that is go to the homework problems and then see which ones you understand.
For sure, that's what I would always do. And I mean, like I think the best way to approach this class is just to keep working through problems, just let a little time go by and then do it again, keep working through them. The class is about those daily problems, basically, is the way I think about it. And so, yeah, to study, if you can find the time to do this, the best thing you could do is go to problem set 1, problem 1, look at it, ask yourself if you know the approach to answering it, and if you do, skip it and keep going until you get to one that you're hazy on. And then spend some time making sense out of that one, and then go on, Every question that I'll ask on tests have similar daily problems that I've already asked you. Yep.
Would you think it's fair to say that like there's some problems that like on the homework that like say we should maybe look at the topic outline, like work of expansion, stuff like that. There might be like some problems that like don't really like, like you might just want to skip that on like some of them homework problems.
I guess there are a couple of things I've said, like you like I've assigned a couple problems where you had to solve differential equations, and I'm not going to make you do that on tests. So there are some things I've said in class where I've tried to sort of de-emphasize some things, but mostly, I mean,
all the outline maybe like that what we just did last.
I think the outline, read through that because it's always good to. I mean, it's always so helpful to have the whole like universe of what we've learned in mind, But really, like for studying for the test, it's just about really understanding the steps that you use for every daily problem. And if you do that, the test will go well. Okay. Any other questions? Okay, so today we're going to start talking about the Rankine power cycle. And there are two useful things about the Rankine power cycle. So two useful things about it. The first one is it's one example of an internally reversible power cycle. So remember that all internally reversible power cycles have the same performance. They have the same efficiency. So since all internally reversible power cycles have the same efficiency, we can use this to derive some of the stuff we've already used about efficiency, about ideal efficiency. So we can use the Rankine power cycle to calculate ideal efficiency. And also we can use this because the definition of entropy comes from internally reversible cycles. We can use this to do calculations related to entropy. Okay, so that's the first thing. This is a specific, like ideal internally reversible cycle that we can use to do calculations. Okay. Second, you've heard mention of a different kind of ideal internally reversible power cycle, the Carnot cycle. We could also do that. So we could study the Carnot power cycle for number one, but the reason we're doing the Rankine cycle instead is the Rankine cycle with some modifications is actually used in power plants. So a modified version of the Rankine power cycle is used in coal-fired plants, oil powered plants, solar, nuclear, biomass. So besides being something theoretical that we can study and gain some insight into what entropy is and ideal performance values, it's also just a practical thing that that describes a lot of how we get power. And the cycle looks like this. So this is the ideal Rankine cycle. The one that you actually see in power plants is not ideal, because you can't make something that's really internally reversible. But we're going to go clockwise around this cycle. So there's a boiler. That then connects to a turbine. Then connects to a condenser. And then connects to a pump. And now we're back at where we started, and it just goes around and around. So I'm going to call this state one. state 2. The states that we're going to consider are in between these processes. So state 2, state 3, and state 4. And you can imagine, so at the turbine, going from state 1 to state 2, we get out some amount of work. That's the whole idea of a power cycle. So the sub T is for turbine. That's the work done by the turbine. Then coming out of the turbine, you have a gas, and you run it through a condenser to turn it into a liquid by extracting heat. So here we're extracting heat at our cold reservoir. After extracting that heat, you have a liquid, but this liquid is at a low pressure. In order to get it into the boiler, you have to get it to a much higher pressure. And so that's what we need the pump for. And in order to run the pump, you need to put some amount of work into the pump. That's electrical work, electrical power. And now in the boiler, this is where we use the nuclear reactions or the the coal fire or whatever to put heat into the working fluid.
So what happens to the heat energy going into up to the cold reservoir? What would that be a power plant? Would that be just just like into the air or something?
Yeah, right. And we'll actually talk about that process some in a few days, but you can think of that as it's like a radiator. There can be, usually there's some kind of cooling fluid wrapped around this condenser that's drawing heat out of the out of the working fluid. So the working fluid is traveling through this pipe, and you're adding heat to it, removing heat from it, running it through a turbine to extract work, running it through the pump. And then as it goes through each one of these devices, something's happening around it to get whatever done that you're trying to have happen.
Use the heat energy
Yeah.
condenser to, I don't know,
Yeah, for sure. And actually, that is something that so often you'll have power plants like this kind of set up in the same area as providers of other types of power. And so the exhaust energy that comes from getting this heat out of the working fluid then gets moved to some other plant or something to use that that hot water for whatever other purpose. So yeah, for sure it does get used. So let's describe these. So we're going to think of 4 stages of this. The first one is the process that goes from state 1 to state 2. Second one from 2 to 3, then 3 to 4, and then 4 back to 1. So from states 1 to 2, now remember this is the ideal Rankine cycle. We're going to talk about corrections to this later to make it realistic. But 1 to 2 is an isentropic expansion through the turbine.
Could you scroll it half a second?
Mm-hmm.
Okay.
And WP is work from pressure?
From the pump. That's the work that you're providing the pump. Like that's the electricity you need to run the pump. So this is through the turbine. And this generates an amount of power WT.
So that turbine would be hooked up to a generator?
Yeah, right. And you could do it to have it hooked up to have a shaft hooked up to something and do it mechanically. But if it's a power plant, then yes, it's hooked up to a generator that's producing electricity. And so the thing to remember here is since this is isentropic, you know that the specific entropy at state 1 is equal to the specific entropy at state 2. Next, going from state 2 to state 3, you have an isobaric heat rejection to the condenser. So this means this is exhaust. And isobaric means the pressure is the same at state 2 as it is at state 3. The pressure stays the same and the temperature decreases, yep. Well, actually, now that I think about it, so the temperature doesn't tend, in the ideal cycle, the temperature stays the same too, because it goes in as mostly a vapor, and it comes out as entirely a saturated liquid. And so if you have a saturated mixture of vapor and liquid, and then you go to a saturated liquid at the same pressure, you're taking a lot of heat out, but the temperature actually isn't changing. Okay? Like water, liquid water at a boiling temperature is the same. Saturated liquid water is the same temperature at standard atmospheric pressure as saturated steam. Okay? Then from 3 to 4, we have another isentropic process. So this is an isentropic pump. To get the liquid to a higher temperature, a higher pressure. And again, isentropic means that the specific entropy at state 3 is equal to the specific entropy at state 4. And then the last stage goes from state 4 to state 1. And that is isobaric again. And that is isobaric heat added at the boiler. Since it's isobaric, the pressures are the same, so pressure at state 4 is equal to the pressure at state 1.